Welcome back to Multigrid Methods. Today we're just going to finish up with a couple of points from chapter 9, and then we're going to go on to chapter 5. Now, you might say, or you might have been, you might think that we finished chapter 5, and we did finish chapter 5 as it was constructed previously, but I added a new section to that. And the reason I did that is so that I could address, in theory, what's going on in chapter 7. So chapter 7 is a whole new chapter which we haven't discussed yet, which describes the multigrid method for cell-centered finite differences. And it's kind of a weird thing. What is cell-centered finite differences, and why does multigrid have to change for that? Well, we'll get into that, and we need to provide a bit of new theory for it. But before we get on to that, I want to, before we get on to what's in 7, we'll do chapter 5, specifically 5.9. And before I do that, I want to wrap up a couple little points that I got wrong in the last lecture. And so, let's see here, I need to adjust my view setting. There we go. And clean up a couple of issues. The first one was the discrete convolution estimate that I had written in my notes way back when by hand in 2014 was absolutely correct. It just turned out that when we transcribed it into LaTeX, somebody got it wrong. I don't know who. There was, so I can take the blame on that, no problem. In any case, it was typed in incorrectly. So now I've fixed that in the notes and in the slides. There should have been a square on this guy and no square here in this sum. So this is like a discrete L1 sum, and this is like a discrete L2 sum. And this is like a convolution in here. This should be squared. That was correct before. So this is like the L2 norm squared of a convolution. And it says that that is going to be less than the square of this L1 sum, this L1 norm of A, times the norm of BJ squared, this, or an L2 norm squared. Now, let me just convince you of this by reminding you of what was Young's inequality for convolutions, because Young's inequality for convolutions proves this thing entirely if you do the right conversion. So here's Young's inequality for convolutions. As long as G is an LP function on the whole real line, and as long as F is an L1 function, meaning it's absolutely integrable on the whole real line, then the convolution is an LP, and that norm of the convolution, LP norm of the convolution, is less than the L1 norm of F times the LP norm of G. In particular, we're going to use this result for P equals 2, and I'm going to square both sides. And if you remember what the 2 norm is, then you'll see what comes out. So for the case P equals 2, upon squaring both sides, then what we get is the integral from minus infinity of the convolution squared, which itself is the integral from minus infinity to infinity, f of x minus y, g of y, dy. So what we do is we integrate out the variables y, and we're left with a function called the convolution. This is called the convolution of f star g, which only depends on x. And of course, we're squaring that, and then we're taking the integral of that as a function of x. Okay, so all this business here is just what we call a convolution. That's a continuous space convolution, or the usual convolution. Now, let's find out what let's find out exactly what Young's inequality says for this guy. What says that you should be less than, because I'm squaring both sides, the L1 norm of F squared times the L2 norm of G squared. So remember, the L2 norm has a square root, but when I square, I get rid of the square root, and so I have the square on the G. So last time I was a bit confused because there seemed to be an imbalance of squares. There wasn't enough squares going around, and so this explains why. I think what I was missing was the square on the G. So that was missing, and that gave rise to the problems. Now, if I define a function f of x to be kind of piecewise and everywhere positive, um, like a step function, I can think about f as being the same as this function or this sequence called a. And if I think about g as a step function, positive everywhere, or non-negative at least, as a step function defined on the blocks of on the unit intervals, 1 to 2, 2 to 3, etc. Unit length intervals, I should say. Then this becomes like a sequence of positive numbers going from minus infinity to plus infinity. So basically, that's the proof of this convolution estimate that we need. And so I'm going to ask you to do this for homework just to ensure that you know exactly what I'm talking about here. But basically, we replace this object here with a discrete convolution inside. And this object here, this L1 norm of f, gets replaced by this, well, I forgot to say L1 norm squared. This is the discrete L1 norm squared here. And this is the discrete L2 norm squared. So it's just exactly that object there. So now, if you use this inequality, this corrected inequality, it's correct now, in the proofs that we did later on for the BPX preconditioner, let me jump ahead a little bit, somewhere around, so what's the maximum? Yeah, so I believe we used it going from here to here. Then it falls out perfectly because what we're going to have is a geometric series for the A series, and the B series is just going to be this guy here. The A series, I misspoke last time. I said this guy has to sum to 1. It doesn't have to exactly sum to 1. It just has to be summable. And it is. It is summable. It's going to be a geometric series, and it works out to have the sum something like, I don't know, 2, 3, 4, something like that, some small number. And so I can, of course, that's just a number which combines with this constant here and makes this constant a little bit bigger. And then I just get two of these guys falling out. And so that's all I really wanted to say about that. The reason why it wasn't coming out before was precisely because I had stated the convolution inequality incorrectly. So now that's corrected, and I think everything's good. All right, any questions before I move on then to chapter 9? Okay, I'm going to go ahead and grab chapter 9. Oops, no, not chapter 9, chapter 5. We're actually moving backwards in time. By the way, for those of you who are local, on Canvas, I've updated all of the slides and the textbook. It's becoming a textbook, I guess. You'll notice the textbook is in rough shape sometimes, and as we're going through it, changing things and fixing things, it's a little bit like a yard being torn up uh, during some sort of spring gardening. It looks like a mess before it looks great in the end. Hopefully, it'll look good. But right now, everything is torn up a bit, and things are a bit scattered. Uh, you can still read it and still, I think, get a lot out of it. But you're seeing how a textbook is put together in real time. If you find any typos or any errors, especially in the chapters that we've previously covered, chapters 1 through 5, 6, 8, and 9, then let me know, please. Chapter 7 is undergoing a bit of reworking, as is as are chapters 10, 11, and there's going to be a new chapter 12 eventually. And then we're going to add some appendices, and that'll be it. But like I said, things are getting a little bit turbulent right now, but they will settle down in the end, and this will be a useful set of notes for you. And then eventually it will be, of course, a book that you can hopefully download it from your library or purchase if you're kind enough to do so. Now, we're in chapter 5, but we're in the very last section of chapter 5 called chapter section 5.9, where we want to discuss what happens when that Galerkin condition fails. So in chapter 6, and chapter 3 to some extent, we were talking a lot about the Galerkin condition, and I kind of hammered that, and I said we really like the Galerkin condition because then the theory is easy. That is all true. Nothing has changed there. But if the Galerkin condition fails, it turns out all hope is not lost. You may still be able to recover convergence, but it may be a little bit harder to get. And 5.9 really hits home on that point. Convergence may still happen, but you may have to spend a lot more time and effort trying to prove convergence, as you'll see. So this is the new part 3 of 3 for chapter 5. And chapter 5 is going through a couple of different iterations on the name. So right now, at this moment in time, it's called Multigrid Algorithms and Abstract Convergence Theory. So that's chapter 5. And I just spoke with Abner today, Dr. Salgado, who came up with an even better title. So very likely this will change. But in any case, chapter 5 will still be numbered the same, just the title of it hasn't been fixed upon yet. All right, so I want to talk about a failure of the Galerkin condition. So in this section, we're going to describe a particular setting where the Galerkin condition fails, and we're going to show that, again, with a little extra effort, we can still salvage multigrid convergence. But we're going to have to work a little bit harder, and things are going to be a little more complicated. Now, with this general theory, which is based on some books by a very famous person named Bramble, Jim Bramble, I think his first name is Jim. He's a long since retired professor who spent many years at Cornell and then moved on to Texas A&M. I'm not sure he's still with us, but he was really well known and really one of the developers of the multigrid theory. So he wrote a book and then an influential article, which is in the Handbook for Numerical Analysis with a former student, I believe, in 2000. And a lot of the material that is present in this chapter is obtained from that source. And now a lot of the things are different from that source. A lot of the styles somewhat similar. So we're going to define a new condition. Now you might remember the old strong Galerkin condition, and what did the strong Galerkin condition say, or what was it about? Well, it said, first of all, the restriction matrix should be equal to the prolongation matrix transpose. And then the coarse grid stiffness matrix should then satisfy the wrap condition, R L minus 1, A L P L minus 1, the strong Galerkin condition, also called the wrap condition. So this is what we call G0, okay? Strong Galerkin condition, the bedrock of a lot of what we did. Now we're going to break the Galerkin condition. We're going to assume that we have a hierarchy of symmetric positive definite matrices, no problem there. But we're going to assume that the prolongation and restriction matrices are no longer related by this simple relation. We're still going to assume, and by the way, I forgot to mention that they have to be full rank matrices, and they're not square typically. They're non-square matrices, but they are full rank. We're going to assume that we have this hierarchy of meshes. Remember, the hierarchy of meshes in chapter 5 was very general. We don't know what these meshes are or mean. We simply think about having this hierarchy of numbers, n0, n1, n2, going all the way up to, there's some abstract one, and that goes all the way up to the top, and the top is n subcapital L. In general, not in general, but typically, we're going to assume that n1 is strictly bigger than n0, n2 is strictly bigger than n1, because why would you do anything differently? It doesn't really make sense to assume differently. So that's what we're going to assume about that. But normally we're going to assume, yes, that these are full rank non-square matrices. And normally for the Galerkin condition, the restriction is the transpose of the prolongation. Now we're not going to assume that anymore. We're going to say the restriction is equal to some constant r times the transpose of the prolongation, where r is some number between 0 and 1. Okay, not so this means we're out of balance. Remember, we said before we had a balanced symmetric pair if r was equal to 1. Well, now we're out of balance. We no longer have this condition. We have this condition where r might be a half or a quarter or something like that. And now for this G3 assumption, which I'm going to call the scaled Galerkin condition, scaled Galerkin. So for this assumption A3, this scaled Galerkin condition, we're not going to have the wrap condition anymore. We're going to have that the stiffness matrix on the coarse grid times 2 is equal to RAP. Okay, the stiffness matrix times 2 is equal to RAP. Or in other words, the coarse grid stiffness matrix is equal to 1/2 of the wrap. So clearly this no longer holds, so we have to give it a new name, and we're going to call this condition G3. All right, condition G3. All of these things are condition G3. All right. Now, if G3 holds, then clearly the strong Galerkin condition must fail. It can't hold anymore. And we also can show that we have this equivalent condition here. So how do we prove this? Well, from the previous, we said that the coarse grid matrix is equal to 1/2 of the wrap, RL minus 1, AL, PL minus 1. All right, but we said that R is equal to R times PL minus 1 transpose, so we can replace that with R over 2, PL minus 1 transpose, A, P, L minus 1. So now we can see clearly that this matrix here, by virtue of the fact that P is, by virtue of the fact that, well, two things. PL minus 1 is full rank matrix, number one. And number two, this is symmetric positive definite. So this matrix here must be symmetric positive definite. Now, if I multiply a constant times a symmetric positive definite matrix, I just get a scaling of the symmetric positive definite matrix. This guy still has to be symmetric positive definite. All right, so now, so what I'm saying is that means that we do not contradict this assumption here. This assumption is not contradicted by these two assumptions. Now, you could say I have a symmetric positive definite matrix family of matrices, and they have to satisfy these two conditions. But it turns out then that AL minus 1 is not symmetric positive definite, or is only symmetric positive definite in certain cases. Well, that would contradict the generality of this definition. But as it is, we're not contradicting that because it's clear that this matrix has to be symmetric positive definite. Okay? But we fail to have the Galerkin condition. Now, let's take this and examine what happens in this case where the Galerkin condition, the strong Galerkin condition, G0, fails, but we only have this scaled Galerkin condition. What happens in this case? Well, one of the things we find out is that the coarse grid Ritz projection matrix, or this thing we called the coarse grid Ritz projection matrix, pi L tilde, also called the paramatrix. So you remember how we kept referring to this guy as the paramatrix. We also called it the coarse grid Ritz projection matrix. Well, maybe the use of this term projection matrix was a little bit premature because if the Galerkin condition fails, this matrix may not be a projection matrix anymore. In fact, in this case, if assumption G3 holds, then this matrix, the power matrix, is no longer a projection matrix. So that means probably should say, use something else here because it's not a projection matrix. Now, I'm not going to go that far. That's draconian. So we're still going to call it the coarse grid rich projection matrix. It's just not going to be actually a projection matrix, if that makes sense. All right, so if it's not a projection matrix, what is it? Well, it's what I would call an almost projection matrix. So if I multiply pi L tilde by itself, so I take pi L squared, then I'm going to get 2 pi L tilde. Remember what we need to have for a projection matrix. Okay, a projection matrix requires that, well, let me do this in more generality. If P is P is a projection matrix if and only if it's a square matrix that satisfies P squared as P. And so this matrix clearly doesn't satisfy that, but it does satisfy this with a 2. So what should I call such a matrix? I'm going to call it an almost projection matrix. Fine. You can call things anything you want to as a mathematician. So so what else do we know about this? Well, it's not a projection matrix, but it is still true based on our construction that it's still AL self-adjoint. In other words, the star of this matrix, the adjoint of this matrix with respect to the AL inner product, is still the original matrix back, pi L tilde. Pi L tilde star is still pi L tilde. So that means it's still self-adjoint in the A1 inner product. So that's a good feature to have, maybe. So it's not a projection matrix anymore, but it is a almost projection matrix, and it is still self-adjoint in the AL inner product. Both of these proofs are simple exercises. All you have to do is multiply this object by itself, and you'll see what you get out in the end using your definitions previously, is that you're going to get 2 pi L tilde. All right, pretty easy. Now, since the coarse grid rich projection is not really a projection, we got to introduce something which is a projection to make our life easier. Now, it turns out this rescaling is fairly simple, or the rescaling that you need to do this is fairly simple. All I'm going to do is I'm going to define this new object called the pi L hat matrix, which is 1/2 pi L tilde. And it turns out this guy is great because this guy is still self-adjoint, and it's also a bona fide projection. Bona fide means good and true. So a bona fide projection matrix, because if I take the square of this matrix, pi hat L by itself, okay, square it with itself. Well, that's the only way you can square something, right? Multiply it by itself, and you get pi L hat out in the end. Okay, so this is a bona fide projection. Bona fide, a Latin phrase. Good and true. All right. Now, if that's true, if pi L hat is a projection matrix that is also self-adjoint, then I minus pi L hat is self-adjoint. Its adjoint is itself. And by adjoint, or the star operation, I mean the adjoint with respect to the AL inner product. And it's also a projection matrix. But this is generally true if I have any projection matrix, then I minus the projection matrix is also a projection matrix. Okay, so probably something that you remember from a linear algebra class, or maybe a numerical analysis class. So the proof of this is a trivial exercise. Shouldn't even have the word exercise there. So trivial. All right, so now let's prove that a version of our two-grid algorithm converges. And to do so, I first need to recall, well, what is the error transfer matrix for the two-grid algorithm? All right. So if you remember, the two-grid algorithm involved pre-smoothing via M1 steps, and then I calculate the residual, push it down through restriction to the lower level. I calculate the coarse grid correction from that and push that up to the fine level. I only have 2 levels in my 2-grid algorithm. And then I do some post smoothing on that M2 times. And if you remember, this might be like you may have to search the cobwebs of your brain to recall this, but my 2-grid error transfer matrix is just this product matrix, product of the error transfer for the pre-smoothing step, error transfer for the coarse grid Ritz projection step. This is no longer a projection though, times the error transfer for the post-smoothing step. And so this object, if we want to prove that the 2-grid method converges, we've got to show that this guy contracts in some norm or is contracted in some norm. All right, so I've also got to recall a couple of definitions that we issued way back when. The first one is called the alpha weak approximation property. So we talked about this, oh gosh, many moons ago, in November, maybe even uh, into October of 2024. We talked about this property called the alpha weak approximation property, also called the A2 property. We say that a multigrid algorithm satisfies the alpha weak approximation property, or equivalently assumption A2, holds if and only if there are constants alpha. Now, alpha has to be between 0 and 1, inclusive of 1, but exclusive of 0. It's not allowed to be 0. And all we know, if it's to satisfy this assumption, that there is some constant alpha and a positive number CA2, such that for every level L between 1 and capital L, and for any UL in RNL, then we have holding this estimate. Okay, so let's look at all of the components here. The first component is IL minus pi L tilde. This is the error for the coarse grid correction or the coarse grid Ritz projection matrix, right? I minus that projection. That's called the error in the projection. All right, so we want to calculate that matrix times an arbitrary UL against UL in the AL inner product. All right, so on the left-hand side, that's the object with absolute values. That's going to be less than a constant, this constant here, some constant CA2 to the 2 alpha power. Okay, so alpha is between 0 and 1. So what does that mean about 2 alpha? So 2 alpha is between 0 and 2, exclusive of 0 and inclusive of 1. What is rho L alpha? Well, that is the precise spectral radius of the AL matrix. Okay, so that guy is the spectral radius of the AL matrix, raised to the alpha power. All right, now we're going to take the canonical L norm of AL times UL, right? This is the Euclidean norm on level L. That's raised to the 2 alpha power. And we have UL in the AL norm. Remember how we define the AL inner product and the AL norm. So the AL inner product is defined as, if I want to calculate AL inner product of U and V, then that is equivalent to ALU. And we don't have to put the L and the L here. Skip that. V in the Euclidean inner product L on level L. And how do I calculate the norm of this guy? Well, I'm going to put the same object here and here. So U and U in both positions, and then I'll take the square root, and that gives me the AL norm. So that's this object here, AL norm of UL, raised to the 2 times 1 minus alpha power. So how big is this guy? Well, alpha could be as big as 1. If alpha is equal to 1,
then 1 minus alpha, of course, is equal to 0. So this is 2 times 0. Alpha equals 1 is actually a special case. So that's kind of what we called um, the weak approximation property. And that was assumption A1, as I recall. Now, in the case where alpha is equal to 1, this term does not appear. This term appears with a square. This term appears as a square, and this term appears as a power 1. So this becomes new and a different property whenever alpha is strictly less than 1. So a common case for us is going to be alpha equals a half. And in the case where alpha equals 1/2, 1 minus alpha is going to be a half times 2 is going to be 1. So this will become the number 1. And 2 times alpha will become the number 1. 2 times alpha will become the number 1. And this will be the square root of the spectral radius on the bottom. This is what was called the alpha weak approximation property, which was introduced way back in section 5.2 or 3, something like this. The other thing we need is something called the first smoothing property or property S1. That's what we're going to use most immediately. We say that a multigrid algorithm satisfies the I said Smurf, didn't I? First smoothing. If you try to say first and smoothing too fast, you end up saying Smurf. That's interesting. Okay. First smoothing property, or equivalently, assumption S1. I should say here, this should be or equivalently S1 holds. So that's a typo. Never get rid of typos. If and only if there is a constant CS1 such that for every L between 1 and L and any UL in RNL, KLM UL in the AL squared norm. What's the AL squared norm? Well, it's defined as the same thing as above here, but instead of using AL, you're going to use AL squared. Okay. So that's like a Sobolev 2 norm or a weight 2 norm, if you know what I mean. If you don't worry about that. We defined that and talked about a long time ago. So that is the 2 norm or this AL squared norm of KLM. What is KLM? KLM was either this guy or this guy. It's the error transfer matrix for smoothing. Okay. Actually, M smoothing iterations in particular. So what we want to show is that in this heavy norm, the error transfer of smoothing, M smoothing steps against or smoothing any vector UL is less than a constant CS1 times rho L to the 1/2 power. Okay, so this rho L to the 1/2 power, what is that? That is our spectral radius, right? Um, Spectral radius rho L, or rho L is the spectral radius. This is the square root of the spectral radius. How does this depend on M? Well, precisely it depends on M by dividing by the square root of M. Okay, so we can't have M equals 0. It doesn't make any sense. All right. In fact, M equals 0, what is that? That is just going to be the identity here. And so I couldn't say anything about this except that this is just going to be um, uh, this estimate breaks down. There's something else different about it, but I'm not really doing anything because I just have the identity against UL. I can't really estimate that and make it smaller. But in this case, what this says is that through smoothing, I can make this norm smaller by doing more smoothing iterations. That's because ultimately I'm dividing, not multiplying by m, I'm dividing by the square root of m. So if I do more smoothing iterations, that means m is getting larger. Let's say I do 100 smoothing iterations, which is impractical, of course, but if I do 100 smoothing iterations, well, then I'm going to get square root of 100 or 10 in the denominator. So that's going to make this whole term on the right-hand side small. All right. So that's really dividing by a power of m. times UL in the AL norm. So that's the norm that we defined through this inner product up above. So these are two properties that we're going to need that I wanted to take a little bit of time to make sure that you understood. Even if you don't recall them specifically, I hope that you understand how fundamental they were to our analysis. So remember, we have these two multigrid properties that we need to fit together in some way in order to make a multigrid algorithm converge. We need a weak, or not a weak, but an approximation property and a smoothing property. So the ones we're going to put together for this scaled Galerkin condition G3 are the alpha weak approximation property and the first smoothing property. Alpha weak approximation and this first smoothing property. We're also going to need, from an earlier part of chapter 5, a stability result. Now, I hope you remember what Richardson's smoother was and how it was defined. So if you need to, you can go back a ways and recall what was Richardson smoother. So Richardson smoother is a certain type of smoother. In some cases, it was exactly the same as the Jacobi iteration method. So if you want to think about it's just Jacobi or weighted Jacobi in a certain sense, then that's fair. That's fine to do that. But Richardson smoother is always going to satisfy. So Richardson smoother, by the way, had a particular choice for its weighting parameter, if you recall. It was a very specific choice for the weighting parameter. Remember, Richardson's method generically is defined with an unspecified weighting parameter. Richardson's smoother has a very specific choice for the weighting parameter in the smoothing step. So uh, now what we're going to establish with this lemma, and this was proven way back in chapter 5, earlier in chapter 5, is what's called a stability result. Namely, if we apply the smoother to any vector VL and we measure that in the norm AL, we can always be guaranteed that the size of this guy is not going to get big. It's, in fact, we can show that it's like less than the norm of the original vector in the same weighting, in the same norm, right? And so, you know, I I think you probably are kind of aware of what's going on here. So now let's suppose that we say that B is stable in some norm, and that norm is what we call an induced norm. So that means we're less than, and I don't care what the norm is, okay? So I'm not going to write down the norm. Just assume that it's some induced norm, right? This is similar to saying that, well, if we knew that B in that norm was less than or equal to 1, then that would certainly imply this stability statement. So this is like an equivalent version of this guy. And it's easy to prove that if I know this. So what am I saying? So if I know this statement on the bottom, then this statement follows. And actually, you can show the converse as well, but I'm not going to worry about that level of detail. But here's the simple proof of the first of what I just said. So I said that I said, if I assume this, then I should get this estimate. Well, remember, any induced norm satisfies submultiplicativity. Or no, let's see. It does satisfy submultiplicativity, but that's not what we need. We need the continuity, right? So we need continuity of norms. So let's use the continuity of norms. And now let's use the fact that B is less than 1 in its matrix norm or its induced norm, and we immediately get that that means that BV is less than V. So you can also go the other way with this, but generally speaking, if I have a stability, it's good to think about something like this. Like the operator is stable in this sense, that I have a norm on that guy. that's exactly what's going on here. Now, the second stability statement is a little bit more complicated, so we won't go into that one. We're just going to observe that it's true and use those properties. The second stability is framed as follows. So KLVL against VL in the canonical inner product on level L, so this is Euclidean inner product, is less than the inner product VL against itself in that same inner product. Well, of course, this is just the norm of V in the canonical norm squared. So I could replace this with the norm squared, and then I could take square roots of both sides. And that says something about the size of the action of this matrix KL. We proved this a long time ago in chapter 5, so I'm not going to prove it again. I just want to recall it to your memory. Now, the first thing we're going to do, and then we'll pause after this and see if there are any questions, but we're going to prove very simply using these two estimates put together that we have the alpha weak convergence of the two-grid method. So here's what I mean. Suppose that I balance pre-smoothing and post-smoothing by setting both M1 and M2 equal to M. Let's assume that our G3 condition and A2 conditions hold. Okay, so G3 condition is the new, what I called scaled Galerkin condition. It's not the strong old Galerkin condition that we are so used to and so love. It's something new. And A2 condition is also going to hold. What was the A2 condition? That's the alpha weak approximation property. This ugly, strange, weird looking object. Now, why are we not assuming that we have the first smoothing property? What happened there? Well, we know that the Richardson smoother automatically satisfies this first smoothing property as long as we have some very basic things that we're working with. And all that we really need is to know what the Richardson smoother is and it's doing. It's a certain type of iterative algorithm based on Richardson's method, where we choose the weighting parameter using the spectral radius in a very judicious way. Well, that method, Richardson's smoother, satisfies the first smoothing property if I do just that. And notice that the smoother doesn't care about the coarse grid. It doesn't even see the coarse grid. Okay, so it's just some action that happens on the fine grid. That's it. There's no L-1 floating around here at all. All right. So that's why we don't have to assume that that the first smoothing property holds, because the first smoothing property automatically holds for Richardson smoother. All right. I hope that I remember to bring that up, but in any case, that's why we're not assuming any smoothing property. So we're going to assume that we use Richardson smoother as our smoother action. So that means we don't have to do anything more. So then we can show that E1, that's the error transfer matrix of the two-grid method, at level 1. So remember, the two-grid, we only have to worry about level 1 and level 0. And so we just have this error transfer matrix for the two-grid algorithm defined at level 1. And it doesn't really matter what level 1 is, it doesn't matter what its size is. We just need to know that there's a fine grid and a coarse grid, and they're related somehow in the usual way through prolongation and restriction, blah, blah, blah. Well, E1, V1, V1 in the A1 inner product, taking absolute value, is less than or equal to the 2 alpha power to the following quotient. CA2 times CS1, quantity divided by the square root of M, times this whole thing times V1, V1 in the A1 inner product. Or in other words, this is just the V1, the norm of V1 in the A1 norm, the A1 norm of V1 squared. So this is enough to ensure convergence, or a contraction of the size of E1 in the A1 metric. It's all about to show you. Now, how do we do all of this? Well, the first thing I want to do is let's let V1 be arbitrary. Anything we want, and we want as a target to show all of this. The first thing I'm going to do is I'm going to use the alpha weak approximation property, which I'm assuming holds. Okay, alpha weak approximation property, which is approximation property A2. This property implies, if I go back and look at this, okay, that this object, I need to look for an object which looks like that against an arbitrary vector. Remember, now I'm working at little l equals 1. All right, but how do I get this vector or this matrix times these vectors here? Well, I'm going to go back all the way to the definition of E1. E1 is the sandwich of K1 star M, because I said M1 and M2 are the same, I1 minus pi 1 tilde times K1 M, M. Well, M1 is equal to M, so these two numbers here are the same. Okay. But notice that E1 has sandwiched inside of it I1 minus pi 1 tilde. Remember, that matrix is no longer equal to a projection matrix, but is still important for us. Now, if I formulate this guy here, then we'll remember what E1 is. It's defined as K1 star to the M2 power times I1 minus pi 1 tilde times K1 to the M power, right? And then I multiply by V1 and I multiply that, or I put that in against V1 in the A1 inner product. Well, I can use the fact that I've got a star here, right? And I'm going to throw that to the other side in my inner product over here. And I'm going to attach it to V1. That symmetrizes things. So what happens when I do that symmetrization process, when I throw that guy to the other side in the A1 inner product, it changes from a K1M star to just K1M. Actually, it's K1M star star, but star star is just the original matrix back. So it becomes K1M. So now K1M V1, K1M V1, that appears, it's kind of like double vision. It's the same vector appearing twice. So I'm going to treat it in exactly the same way. But now look, once I moved that guy over to the other side in this A1 inner product, now I have something which I can apply my A2 property to, the alpha weak approximation property. That says that I'm less than whatever vector this is, some complicated constant where alpha is, remember, alpha has to be some number between 0 and 1, not inclusive of 0, but inclusive of possibly of 1. So whatever vector this is, it gets multiplied by A1, and we take the 1 norm of that, and we raise it to the 2 alpha power. Okay, so what appeared previously here is a generic vector. Well, now that's going to be K1MV1. K1MV1 appears there and there. Okay, so this is just exactly A2, property A2, the alpha weak approximation property. It's just exactly that after having moved this guy. All right, so let's look at this for a second. Remember, this is going to be the spectral radius of A1. This is some constant. Alpha is some number between 0 and 1. And you can just think about it being a half for now. That's fine. All right, now what am I going to do? What's the next thing I'm going to do? Well, I've applied alpha weak approximation. Maybe the next thing to do is apply a smoothing property. So next, we're going to recall that Richardson smoother satisfies assumption S1 just on face value. That's because of the structure of it, and it doesn't really care that the Galerkin condition changes. It has nothing to do with Galerkin. So as long as I'm using Richardson smoother, it's going to satisfy assumption S1. Using this fact and then the stability of Richardson's method and the alpha weak approximation property again, which we used previously. So alpha weak approximation gave me that. That was just from the previous page. All right. Now, this, what am I doing here? What am I getting? I'm just using here the stability of this guy in the A1 norm. Okay, so let's go back and look at the stability that I'm using. I'm using that stability so I can get rid of this guy in that location. So that's the one I'm using. But I'm using it at level L equals 1. At level L equals 1, I'm using that to get rid of this KL. The reason why I'm using it is because I need this to work out to be a V1 in the end. Now, the next thing I'm going to do is just realize that if I have an A1 here in the 1 norm, that's exactly, turns out, exactly the same norm as this guy. And I hope you can convince yourself of that. Just do a little calculation. Actually, let's do that. We'll do it together after I finish this argument. All right, so now I recognize that that's just exactly the norm that I have and need in my smoothing property. And I know that the Richardson smoother satisfies assumption S1. And so I'm going to apply that here. So I apply S1 here. So this tells me that I can reduce the size of this guy by replacing this. Now it comes at the 2 alpha power. So what I have to do in that S1, I have to multiply 2 alpha, 2 alpha, 2 alpha, 2 alpha, right? I have to take everything to the 2 alpha power when I do that. So you see when I do that, there's no alpha involved in this in sight, and it's going to gain a bunch of 2 alphas. Okay, so when I do that, S1 gets raised to the 2 alpha power. Um, Rho 1 gets raised to the alpha power. M gets raised to the minus alpha power because I'm taking everything to the 2 alpha power because of this. All right, so um, what does that say? Plus, oh, I can't forget something else. So there's also another factor precisely of V1 or the norm of V1 in the A1 norm of the exactly the right power so that when I add the powers together, this 2 alpha or 2, 1 minus 2 alpha becomes 2. In other words, I'm going to multiply this guy, V1, A1, 2 alpha times V1, 2 minus 2 alpha, and the 2 alpha and the 2 alpha here cancel, and it just gives me V1 squared in the A1 norm. I forgot to write A1. So that's why I get an A1 norm here. Now, what else do I have? And this would not have happened if I wouldn't have used the stability to get rid of this K. I had to use the stability to eliminate that and going from this step to that. And then I have precisely the right powers that cancel just to give me the square. That's good. Now, what else do I have? Well, I can cancel these two. I need those to cancel. I absolutely need these guys to cancel in order for my analysis to work. Now, these two things both have a 2 alpha power. This is m to the minus alpha. I can raise that to a 2 alpha power by moving that to the bottom and replacing the minus 1 by a minus 1/2, or in other words, putting it in the denominator and just taking the square root of m. And then you can see that 2 alpha power of this quotient just gives me exactly all that. This is another way of saying the A1 inner product V1 times V. And the only reason I did that is because that's exactly what I was looking for in this result. All right. So that's precisely the convergence result that I wanted to prove. Why is it a convergence result? Well, this says that I can make this number smaller than 1 as long as I make m large enough. As long as I make m large enough, I can make this whole number less than 1, right? Do you believe that? So let's suppose that the product of this guy is is equal to 5, then to make this smaller than 1 on the bottom, this quotient smaller than 1, I just have to make m to the 1/2 power bigger than 5. So if I make it 6, that would work. So if I take 36 smoothing iterations, take the square root of that, that gives 6, 5 over 6. If I raise 5 over 6 to the 2 alpha power, I'm going to get a number which is still less than 1. So I'm good. I'm happy. I get a convergence result. Now, how do I know that it's a convergence result? Well, I can take the result that I got from the last theorem and I can do a little bit of analysis for it. I'm going to assign this as a homework problem just so you can recall what's going on here. But that previous result, using the fact that E1, I think it only uses the fact that E1 is self-adjoint in the A1 inner product. And then I can use some eigenvalue type of arguments to argue that the result that I just had can be translated into this result here. So the constant is the same. The constant is the same. The square that was here goes away, and this is like something with the square that could go away. And so finally, I can just get this result. The proof is an exercise. All right, so now I want to prove a harder result. We just proved that the two-grid algorithm converges. That's great. But the two-grid algorithm is not the end-all be-all, right? So really, multigrid flies whenever we can use it in this recursive multi-level structure, and we can eliminate then, what does the two-grid algorithm require that's not quite practical? Well, the two-grid algorithm requires the not so practical step that on the coarse grid, you have to solve the problem exactly. And so if you can't do that, or it's impractical to do that, or you want to do something more efficient than doing that, then we have to use a recursion type of argument and a recursion type of algorithm. So remember, we created these things called the V cycle, the W cycle, and the P cycle, the generic P cycle. And to do that, we had to define a more complicated error transfer matrix, blah, blah, blah. Lots of more complicated stuff that we won't be able. Well, so that was defined earlier in chapter 5. I might bring it back to your uh, recollection exactly what is the definition of that. Um, but um, but for now, you can just think we defined this thing, error transfer matrix, for the generic P cycle, and so, or I guess we called that a W cycle. Um, and we defined this thing, and so now we want to prove a few um, properties with it. We had to show previously when we were doing the W cycle and the V cycle, whenever we could assume we had the Galerkin condition intact, what did we do? We tried to show, well, using the approximation property, the Galerkin condition, and the smoothing properties, we tried to show that we could control the size of the error transfer matrix in an energy norm. And so to that end, that's I want to give some estimates on the error transfer matrix that still hold even in the case where the G3 condition doesn't hold. Now, the reason why this is a big problem is because whenever we assume G0 condition holds, then we could take advantage of the fact that the I minus pi L tilde matrix was a projection matrix. And that gave us a lot of leverage. Now we've lost that. And so when we have G3, we have to work a bit harder. Okay, so what I'm going to do now is prove a little technical, a series of technical lemmas, state them. I might prove some of them, might ask you to prove some of them. But in any case, we'll go through a few of these technical lemmas that we're going to need to prove that the generic W cycle algorithm converges. So that's the very first thing we want to do. And then finally, we want to come back and show that a special form of the V cycle converges And this is a stronger convergence result, which says that the W cycle converges um, for any amount of smoothing that you want to do to the problem. So um, what we won't prove, unfortunately, is that the V cycle converges. We'll only be able to prove that the W cycle converges. First, sort of a weaker result, and then a stronger result that shows the W cycle converges for any amount of smoothing that you throw at this problem using Richardson smoother. So let's get into it. So the thing we're going to assume about all of the W cycle algorithms in this section is that they are symmetrized. So symmetrization means that we can use the fact that the EL matrix is self-adjoint, and so that is very important. In fact, it's important in this proof right here. So you have to use, and if you want to make a note of this for later, the fact that the algorithm is symmetrized is going to mean that E1 is self-adjoint with respect to the A1 inner product. Okay, E1 star is equal to E1. So again, here we're going to use that fact somewhere that EL star is equal to EL, but in the generic, on a generic level. This doesn't require our coarse grid Ritz projection matrix to be a projection. It just is always going to be true as long as we're symmetrized. Symmetrization means we're going to set M1 equal to M2. Okay, so that's the first step. P is just going to be a cycle number. Uh, I think we call it anything where P is bigger than 1 a W cycle. Sometimes people call that a P cycle, and they call a W cycle just is strictly speaking P equals 2. I got to go back and make sure that I've been consistent with that nomenclature and convention in the book, but let me know if I haven't been. But in any case, P equals 2 is usually what's called the W cycle, but I believe here in this book we call anything where P is greater than 1 the W cycle. All right, so the error transfer matrix is self-adjoint with respect to the AL inner product. In fact, we already proved that and know that, and still holds true, even though that our coarse grid Ritz projection matrix is no longer truly a projection. That's still true. This is still true. Furthermore, if there is a number gamma greater than 0 such that for all VL in RNL, EL, VL, VL in the AL inner product, absolute value, is less than gamma times VL, VL, AL. So this is the AL inner product of VL against itself. So this is the AL norm of VL squared. So if this is true for some gamma, then if I raise EL to the P power, so that's P applications of the error transfer matrix at level L, then this is going to be less this object here, which is the same as this object on the top, except for the P is the 1 here becomes a P. I can replace this gamma over here with a gamma to the P power. That's a good thing because usually I'm going to make gamma small, and so gamma to the P is going to be a lot smaller. Okay, so that's saying if I do P applications of the error transfer matrix at level L, in other words, I do P iterations of whatever recursive algorithm I'm doing. If I could get gamma over here for one application, I can get gamma to the P where gamma is small for P applications. If P is even, then EL is in addition positive semi-definite with respect to the AL inner product, meaning that I can show that EL to the P power, VL times AL is greater than or equal to 0. And the reason I can do that is technical. It's precisely because I can use the fact that I have the AL inner that I have that EL is self-adjoint with respect to the AL inner product. Then I can take half of it from here and I can move it over to here, and then you can see that it just, and since you're in the AL inner product, and since you can do that, then I have the same thing appearing here as I have over here, and so that object has to, because of the properties of the inner product, that object always has to be greater than or equal to 0. All right, we're going to leave it for you as an exercise, you the reader, you the audience member, to confirm that EL is self-adjoint with respect to the AL inner product. In fact, I claim that that's already been done for you. There's nothing else to do, um, because you can use more or less some previous calculations that we've already done. Um, I guess we didn't exactly do it because previously I think we may have assumed that we had a balanced prolongation restriction operator. But you can correct me if I'm wrong on that one. In any case, I want you to go through and do it in the homework, and see how this works out. If, however, you can prove this, if EL is self-adjoint with respect to the AL inner product, then there's an orthonormal basis of eigenvectors with respect to the AL inner product, and the eigenvalues have to always be real. So now what you can do is you can expand VL in this basis. So take EL in this basis, and then you're just going to do some estimates. And then so if I do that, use some estimates, basically I already know that's happening there. I'm going to assume that. So this is the thing I want to estimate. So I'm going to start with this guy. If I know that this is symmetric positive definite, then also any power p is also going to have the same thing, and moreover, it's going to have the same set of eigenvectors. So I can use that fact, and then I'm going to expand, as I said, VL in the basis of these eigenvectors, and I'm going to estimate. And so the details of the proof are going to also be left as an exercise. So there's really two main things to do. This one I claim is done or almost done based on work that we did previously in the chapter. And then the only thing that you have to do, which is new, is to expand this VL in the basis of eigenvectors and estimate. Okay, so I'm going to leave those details uh, as an exercise. By the way, that's the same technique that I'm going to use here. I'm gonna try to show that this being less than this implies this is true, and the methodology that I'm going to use is more or less the same. Since this guy is going to be self-adjoint, I'm going to expand V1 in a basis of eigenvectors of E1, okay, or E1 star, they're the same. And then I'm going to use this estimate that I had previously and try to get the result. In fact, what you can do is just start off with the expansion of V1 here, carry that forward, and you'll find that it's not much more than a few steps to get this. But I do require that I have a symmetrized form, and I'm able then to take advantage of the fact that this is self-adjoint. The same thing I'm going to do here. Okay, I'm going to use this fact, use the fact that I have a symmetrized method. Therefore, EL is self-adjoint with respect to um, the AL inner product. And then I'm going to expand VL in a basis and estimate using this information that I have from above. All right, so those are the two steps that are left for your proof. Any questions about that? Okay, so another technical estimate, and I think we'll probably prove this one, and then I doubt we can get on to these guys. So we'll prove this guy, hope that you understand that, and that'll be the last technical estimate that we'll use. Somewhere in this area, we're going to prove that the W cycle converges, and then somewhere here, we're going to give an improved convergence give an improved convergence estimate or convergence proof, blah, blah, blah. I don't know exactly which for the W cycle. Now, the one thing that we're not going to prove is there's no proof that the V cycle method is converging. Sadly, well, not sadly, I guess, excitingly, this is an open question that we have not yet answered. So, if you're interested in a interesting research project, then that may be it. All right, so first things first, let's prove this estimate here. All right, so now pi L tilde is not a projection matrix. So we have to be crafty in certain locations, um, and establish some other wonky, weird, wild estimates that are going to be useful to us in some way, shape, or form later on. All right, but the fact that we break the fact, well, let's see, don't want to use fact too many times. The fact that pi L tilde and I minus pi L tilde are no longer projection matrices is going to make life difficult for us. So let's use something that we do know. We do know that pi L hat is a projection matrix, and so the fact that this is so is going to be or allow us to prove this estimate, which doesn't look helpful, admittedly, but is going to be quite helpful. So let's assume that G3 holds. Remember, that's our scaled Galerkin condition. If that holds, then for any L between 1 and capital L and any VL that you want to choose, then we have this estimate holding minus the quantity IL minus pi L times VL against VL, and the AL inner product is less than VL times VL in the AL inner product. Now, the first thing you might ask yourself is, why do I have the minus sign here? Why didn't I just take the absolute value? Well, the answer is, well, I can only prove this for the minus sign, but that's all I'm going to need. Now, this object here, I don't know what the sign of this guy is going to be. It could be positive, it could be negative, I don't know. Um, So that's because I don't know that this is a projection matrix. If it was a projection matrix, then I could replace this object by its square. I could throw half the thing to the other side, and I could show that this object in here is actually greater than or equal to 0. So that would tell me the sign on this guy would say the sign on this guy, whole thing, would be negative. Right now, I don't know. I don't know what is the sign on this guy because this is not a projection matrix. All right, so I have to do something different. But I ultimately, it's enough, or it's going to be enough for me to show that the negative of this object is less than this object. So how do I prove that? I'm going to use the fact that this guy here is a projection matrix. Okay, and it's also self-adjoint with respect to the AL inner product. So I know that this object here is a norm squared, just by not by definition, but by properties of norms, right? Norm of anything squared times 2 is going to be greater than 0, greater than or equal to 0. Now, what is the definition of this? This is just the AL inner product of this vector against itself. So there and there. But this object here, I can move this to the other side, right? And I know that when it moves to the other side, it moves with a star, but it's self-adjoint, so it becomes a square. Uh-oh, that is, this should be pushed back this way. Not sure how that leaked out, but that's should be there should be alignment here. Not sure what happened. Okay. Um, yes, now I do know what happened. I screwed this up. I removed the aligners from this, but I'll fix that. Okay, so you're going from this equal sign down to here. I'm going to take this guy, move it to the other side. It becomes a square. But remember, this is a projection matrix because I'm using the hat matrix, not the tilde matrix. So it comes back over, use the fact that it's a projection matrix, so I can replace that with the square with IL minus pi L hat, VL in the AL inner product. All right, so now follow the chain of equalities now. Equality to here. What am I doing in going from here to here? I'm just using the definition of the pi L hat matrix. Remember, it's 1/2 of the pi L tilde matrix. Now I'm going to use the fact that I can break this guy up into IL and IL, or in other words, this whole sum is IL minus pi L tilde plus IL, and then use the linearity of the AL in a product to break this into the sum of these two objects here. Now I'm just going to take this object here, and remember, zeros on the left-hand side is going to move this guy over to the left-hand side by subtracting it off, and I ultimately just get this. Okay, after I move it over from the right-hand side, it attains this minus sign. And so QED done. All right, so I'm going to stop there. And we'll pick up with these technical lemmas next time. I've got a few more to prove before we get on to our first big result, the alpha weak convergence of the W cycle. All right, I'll stop there and I'll take any questions that you guys have.